This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recorded by Julian Jameson. The Concept of Nature by Alfred North Whitehead. Section 8. Summary. There is a general agreement that Einstein's investigations have one fundamental merit, irrespective of any criticisms which we may feel inclined to pass on them. They have made us think. But when we have admitted so far, we are most of us faced with a distressing perplexity. What is it that we ought to think about? The purport of my lecture this afternoon will be to meet this difficulty, and so far as I am able to set in a clear light the changes in the background of our scientific thought which are necessitated by any acceptance, however qualified, of Einstein's main positions. I remember that I am lecturing to the members of a chemical society who are not for the most part versed in advanced mathematics. The first point that I would urge upon you is that what immediately concerns you is not so much the detailed deductions of the new theory, as this general change in the background of scientific conceptions, which will follow from its acceptance. Of course, the detailed deductions are important, because unless our colleagues, the astronomers and the physicists, find these predictions to be verified, we can neglect the theory altogether. But we may now take it as granted that in many striking particulars these deductions have been found to be in agreement with observation. Accordingly, the theory has to be taken seriously, and we are anxious to know what will be the consequences of its final acceptance. Furthermore, during the last few weeks, the scientific journals and the lay press have been filled with articles as to the nature of the crucial experiments which have been made, and as to some of the more striking expressions of the outcome of the new theory. "Space caught bending" appeared on the news sheet of a well-known evening paper. This rendering is a terse but not inapt translation of Einstein's own way of interpreting his results. I should say at once that I am a heretic as to this explanation, and that I shall expound to you another explanation based upon some work of my own, an explanation which seems to me to be more in accordance with our scientific ideas, and with the whole body of facts which have to be explained. We have to remember that a new theory must take account of the old, well-attested facts of science, just as much as of the very latest experimental results which have led to its production. To put ourselves in the position to assimilate and to criticize any change in ultimate scientific conceptions, we must begin at the beginning. So you must bear with me if I commence by making some simple and obvious reflections. Let us consider three statements. 1. Yesterday a man was run over on the Chelsea embankment. 2. Cleopatra's Needle is on the Charing Cross embankment. And 3. There are dark lines in the solar spectrum. The first statement about the accident to the man is about what we may term an occurrence, a happening, or an event. I will use the term event because it is the shortest. In order to specify an observed event, the place, the time, and character of the event are necessary. In specifying the place and the time, you are really stating the relation of the assigned event to the general structure of other observed events. For example, the man was run over between your tea and your dinner, and adjacently to a passing barge in the river and the traffic in the Strand. The point which I want to make is this: nature is known to us in our experience as a complex of passing events. In this complex we discern definite mutual relations between component events, which we may call their relative positions, and these positions we express partly in terms of space and partly in terms of time. Also, in addition to its mere relative position to other events, each particular event has its own peculiar character. In other words, nature is a structure of events, and each event has its position in this structure and its own peculiar character or quality. Let us now examine the other two statements in the light of this general principle as to the meaning of nature. Take the second statement. Cleopatra's Needle is on the Charing Cross embankment. At first sight, we should hardly call this an event. It seems to lack the element of time or transitoriness. But does it? If an angel had made the remark some hundreds of millions of years ago, the earth was not in existence. 20 millions of years ago there was no Thames. 80 years ago there was no Thames embankment. And when I was a small boy, Cleopatra's Needle was not there. and now that it is there, we none of us expect it to be eternal. The static, timeless element in the relation of Cleopatra's Needle to the embankment is a pure illusion, generated by the fact that for purposes of daily intercourse its emphasis is needless. What it comes to is this: amidst the structure of events which form the medium within which the daily life of Londoners is passed, we know how to identify a certain stream of events which maintain permanence of character, namely the character of being the situations of Cleopatra's Needle. Day by day and hour by hour we can find a certain chunk in the transitory life of nature, and of that chunk we say, "There is Cleopatra's Needle." If we define the needle in a sufficiently abstract manner, we can say that it never changes. But a physicist who looks on that part of the life of nature as a dance of electrons will tell you that daily it has lost some molecules and gained others, and even the plain man can see that it gets dirtier and is occasionally washed. Thus the question of change in the needle is a mere matter of definition. The more abstract your definition, the more permanent the needle. But whether your needle change or be permanent, all you mean by stating that it is situated on the Charing Cross embankment is that amid the structure of events you know of, a certain continuous limited stream of events, such that any chunk of that stream, during any hour or any day or any second, has the character of being the situation of Cleopatra's Needle. Finally, we come to the third statement. There are dark lines in the solar spectrum. This is a law of nature. But what does that mean? It means merely this: if any event has the character of being an exhibition of the solar spectrum under certain assigned circumstances, it will also have the character of exhibiting dark lines in that spectrum. This long discussion brings us to the final conclusion that the concrete facts of nature are events exhibiting a certain structure in their mutual relations and certain characters of their own. The aim of science is to express the relations between their characters in terms of the mutual structural relations between the events thus characterized. The mutual structural relations between events are both spatial and temporal. If you think of them as merely spatial, you are omitting the temporal element, and if you think of them as merely temporal, you are omitting the spatial element. Thus, when you think of space alone, or of time alone, you are dealing in abstractions. Namely, you are leaving out an essential element in the life of nature as known to you in the experience of your senses. Furthermore, there are different ways of making these abstractions which we think of as space and as time, and under some circumstances we adopt one way, and under other circumstances we adopt another way. Thus there is no paradox in holding that what we mean by space under one set of circumstances is not what we mean by space under another set of circumstances. And equally, what we mean by time under one set of circumstances is not what we mean by time under another set of circumstances. By saying that space and time are abstractions, I do not mean that they do not express for us real facts about nature. What I mean is that there is no spatial facts or temporal facts apart from physical nature, namely that space and time are merely ways of expressing certain truths about the relations between events. Also, that under different circumstances there are different sets of truths about the universe which are naturally presented to us as statements about space. In such a case, what a being under the one set of circumstances means by space will be different from that meant by a being under the other set of circumstances. Accordingly, when we are comparing two observations made under different circumstances, we have to ask, do the two observers mean the same thing by space and the same thing by time? The modern theory of relativity has arisen because certain perplexities as to the concordance of certain delicate observations, such as the motion of the earth through the ether, the perihelion of Mercury, and the positions of the stars in the neighborhood of the sun, have been solved by reference to this purely relative significance of space and time. I want now to recall your attention to Cleopatra's Needle, which I have not yet done with. As you are walking along the embankment, you suddenly look up and say, "Hello, there's the needle." In other words, you recognize it. You cannot recognize an event, because when it is gone, it is gone. You may observe another event of analogous character, but the actual chunk of the life of nature is inseparable from its unique occurrence. But a character of an event can be recognized. We all know that if we go to the embankment near Charing Cross, we shall observe an event having the character which we recognize as Cleopatra's Needle. Things which we thus recognize I call objects. An object is situated in those events or in that stream of events of which it expresses the character. There are many sorts of objects. For example, the color green is an object according to the above definition, It is the purpose of science to trace the laws which govern the appearance of objects in the various events in which they are found to be situated. For this purpose we can mainly concentrate on two types of objects, which I will call material physical objects and scientific objects. A material physical object is an ordinary bit of matter, Cleopatra's Needle, for example. This is a much more complicated type of object than a mere color, such as the color of the needle. I call these simple objects, such as colors or sounds, sense objects. An artist will train himself to attend more particularly to sense objects, where the ordinary person attends normally to material objects. Thus, if you were walking with an artist, when you said, "There's Cleopatra's Needle," perhaps he simultaneously exclaimed, "There's a nice bit of color." Yet you were both expressing your recognition of different component characters of the same event. But in science we have found out that when we know all about the adventures amid events of material physical objects and of scientific objects, we have most of the relevant information which will enable us to predict the conditions under which we shall perceive sense objects in specific situations. For example, when we know that there is a blazing fire, i.e., material and scientific objects undergoing various exciting adventures amid events, and opposite to it a mirror, which is another material object, and the positions of a man's face and eyes gazing into the mirror, we know that he can perceive the redness of the flame situated in an event behind the mirror. Thus, to a large extent, the appearance of sense objects is conditioned by the adventures of material objects. The analysis of these adventures makes us aware of another character of events, namely their characters as fields of activity, which determine the subsequent events to which they will pass on the objects situated in them. We express these fields of activity in terms of gravitational, electromagnetic, or chemical forces and attractions. But the exact expression of the nature of these fields of activity forces us intellectually to acknowledge a less obvious type of objects as situated in events. I mean molecules and electrons. These objects are not recognized in isolation. We cannot well miss Cleopatra's Needle if we are in its neighborhood, but no one has seen a single molecule or a single electron. Yet the characters of events are only explicable to us by expressing them in terms of these scientific objects. Undoubtedly molecules and electrons are abstractions, but then so is Cleopatra's Needle. The concrete facts are the events themselves. I have already explained to you that to be an abstraction does not mean that an entity is nothing. It means merely that its existence is only one factor of a more concrete element of nature. So an electron is abstract, because you cannot wipe out the whole structure of events and yet retain the electron in existence. In the same way, the grin on the cat is abstract, and the molecule is really in the event in the same sense as the grin is really on the cat's face. Now, the more ultimate sciences, such as chemistry or physics, cannot express their ultimate laws in terms of such vague objects as the sun, the earth, Cleopatra's Needle, or a human body. Such objects more properly belong to astronomy, to geology, to engineering, to archaeology, or to biology. Chemistry and physics only deal with them as exhibiting statistical complexes of the effects of their more intimate laws. In a certain sense, they only enter into physics and chemistry as technological applications. The reason is that they are too vague. Where does Cleopatra's Needle begin, and where does it end? Is the soot part of it? Is it a different object when it sheds a molecule, or when its surface enters into chemical combination with the acid of a London fog? The definiteness and permanence of the needle is nothing to the possible permanent definiteness of a molecule, as conceived by science, and the permanent definiteness of a molecule in its turn yields to that of an electron. Thus science, in its most ultimate formulation of law, seeks objects with the most permanent definite simplicity of character, and expresses its final laws in terms of them. Again, when we seek definitely to express the relations of events which arise from their spatio-temporal structure, we approximate to simplicity by progressively diminishing the extent, both temporal and spatial, of the events considered. For example, the event which is the life of the chunk of nature, which is the needle, during 1 minute, has to the life of nature within a passing barge during the same minute a very complex spatio-temporal relation. But suppose we progressively diminish the time considered to a second, to 1/100th of a second, to 1,000th of a second, and so on. As we pass along such a series, we approximate to an ideal simplicity of structural relations of the pairs of events successively considered, which ideal we call the spatial relations of the needle to the barge at some instant. Even these relations are too complicated for us, and we consider smaller and smaller bits of the needle and of the barge. Thus we finally reach the ideal of an event so restricted in its extension as to be without extension in space or extension in time. Such an event is a mere spatial point flash of instantaneous duration. I call such an ideal event an event particle. You must not think of the world as ultimately built up of event particles. That is to put the cart before the horse. The world we know is a continuous stream of occurrence which we can discriminate into finite events, forming by their overlappings and containings of each other, and separations, a spatio-temporal structure. We can express the properties of this structure in terms of the ideal limits to roots of approximation, which I have termed event particles. Accordingly, event particles are abstractions in their relations to the more concrete events. But then by this time you will have comprehended that you cannot analyze concrete nature without abstracting. Also, I repeat, the abstractions of science are entities which are truly in nature, though they have no meaning in isolation from nature. The character of the spatio-temporal structure of events can be fully expressed in terms of relations between these more abstract event particles. The advantage of dealing with event particles is that though they are abstract and complex in respect to the finite events which we directly observe, they are simpler than finite events in respect to their mutual relations. Accordingly, they express for us the demands of an ideal accuracy, and of an ideal simplicity in the exposition of relations. These event particles are the ultimate elements of the four-dimensional space-time manifold, which the theory of relativity presupposes. You will have observed that each event particle is as much an instant of time as it is a point of space. I have called it an instantaneous point flash. Thus in the structure of this space-time manifold, space is not finally discriminated from time, and the possibility remains open for diverse modes of discrimination according to the diverse circumstances of observers. It is this possibility which makes the fundamental distinction between the new way of conceiving the universe and the old way. The secret of understanding relativity is to understand this. It is of no use rushing in with picturesque paradoxes, such as space-caught bending, if you have not mastered this fundamental conception which underlies the whole theory. When I say that it underlies the whole theory, I mean that in my opinion it ought to underlie it, though I may confess some doubts as to how far all expositions of the theory have really understood its implications and its premises. Our measurements, when they are expressed in terms of an ideal accuracy, are measurements which express properties of the space-time manifold. Now there are measurements of different sorts. You can measure lengths, or angles, or areas, or volumes, or times. There are also other sorts of measures, such as measurements of intensity of illumination, but I will disregard these for the moment, and will confine attention to those measurements which particularly interest us as being measurements of space or of time. It is easy to see that 4 such measurements of the proper characters are necessary to determine the position of an event particle in the space-time manifold in its relation to the rest of the manifold. For example, in a rectangular field you start from one corner at a given time. You measure a definite distance along one side. You then strike out into the field at right angles, and then measure a definite distance parallel to the other pair of sides. You then rise vertically a definite height, and take the time. At the point and at the time which you thus reach, there is occurring a definite, instantaneous point flash of nature. In other words, your 4 measurements have determined a definite event particle belonging to the 4-dimension space-time manifold. These measurements have appeared to be very simple to the land surveyor, and raise in his mind no philosophical difficulties. But suppose there are beings on Mars, sufficiently advanced in scientific invention to be able to watch in detail the operations of this survey on Earth. Suppose that they construe the operations of the English land surveyors in reference to the space natural to a being on Mars, namely a Martiocentric space, in which that planet is fixed. The Earth is moving relatively to Mars, and is rotating. To the beings on Mars, the operations construed in this fashion effect measurements of the greatest complication. Furthermore, according to the relativistic doctrine, the operation of time measurement on Earth will not correspond quite exactly to any time measurement on Mars. I have discussed this example in order to make you realize that in thinking of the possibilities of measurement in the space-time manifold, we must not confine ourselves merely to those minor variations which might seem natural to human beings on the Earth. Let us make therefore the general statement that 4 measurements, respectively of independent types, such as measurements of lengths in 3 directions and a time, can be found such that a definite event particle is determined by them in its relations to other parts of the manifold. If P1, P2, P3, P4 be a set of measurements of this system, then the event particle which is thus determined will be said to have P1, P2, P3, P4 as its coordinates in this system of measurement. Suppose that we name it the P system of measurement. Then in the same P system, by properly varying P1, P2, P3, P4, every event particle that has been, or will be, or instantaneously is now, can be indicated. Furthermore, according to any system of measurement that is natural to us, 3 of the coordinates will be measurements of space, and 1 will be a measurement of time. Let us always take the last coordinate to represent the time measurement. Then we should naturally say that P1, P2, P3 determined a point in space, and that the event particle happened at that point at the time P4. But we must not make the mistake of thinking that there is a space in addition to the space-time manifold. That manifold is all that there is for the determination of the meaning of space and time. We have got to determine the meaning of a space point in terms of the event particles of the 4-dimensional manifold. There is only one way to do this. Note that if we vary the time, and take times with the same 3 space coordinates, then the event particles, thus indicated, are all at the same point. But seeing that there is nothing else except the event particles, this can only mean that the point P1, P2, P3 of the space in the P system is merely the collection of event particles P1, P2, P3, bracket P4, where P4 is varied, and P1, P2, P3 is kept fixed. It is rather disconcerting to find that a point in space is not a simple entity, but it is a conclusion which follows immediately from the relative theory of space. Furthermore, the inhabitant of Mars determines event particles by another system of measurements. Call his system the Q system. According to him, Q1, Q2, Q3, Q4 determines an event particle, and Q1, Q2, Q3 determines a point, and Q4 a time. But the collection of event particles which he thinks of as a point is entirely different from any such collection which the man on Earth thinks of as a point. Thus the Q space for the man on Mars is quite different from the P space for the land surveyor on Earth. So far, in speaking of space, we have been talking of the timeless space of physical science, namely of our concept of eternal space, in which the world adventures. But the space which we see as we look about is instantaneous space. Thus, if our natural perceptions are adjustable to the P system of measurements, we see instantaneously all the event particles at some definite time P4, and observe a succession of such spaces as time moves on. The timeless space is achieved by stringing together all these instantaneous spaces. The points of an instantaneous space are event particles, and the points of an eternal space are strings of event particles occurring in succession. But the man on Mars will never perceive the same instantaneous spaces as the man on Earth. This system of instantaneous spaces will cut across the Earth-man system. For the Earth-man, there is one instantaneous space which is the instantaneous present. There are the past spaces and the future spaces. But the present space of the man on Mars cuts across the present space of the man on Earth. So that of the event particles which the Earth-man thinks of as happening now in the present, the man on Mars thinks that some are already past, and are ancient history, that others are in the future, and others are in the immediate present. This breakdown in the neat conception of a past, a present, and a future is a serious paradox. I call 2 event particles which on some or other system of measurement are in the same instantaneous space co-present event particles. Then it is possible that A and B may be co-present, and that A and C may be co-present, but that B and C may not be co-present. For example, at some inconceivable distance from us there are events co-present with us, now, and also co-present with the birth of Queen Victoria. If A and B are co-present, there will be some systems in which A precedes B, and some in which B precedes A. Also, there can be no velocity quick enough to carry a material particle from A to B or from B to A. These different measure systems, with their divergences of time reckoning, are puzzling, and to some extent affront our common sense. It is not the usual way in which we think of the universe. We think of one necessary time system and one necessary space. According to the new theory, there are an indefinite number of discordant time series and an indefinite number of distinct spaces. Any correlated pair, a time system and a space system, will do in which to fit our description of the universe. We find that under given conditions our measurements are necessarily made in some one pair which together form our natural measure system. The difficulty as to discordant time systems is partly solved by distinguishing between what I call the creative advance of nature, which is not properly serial at all, and any one time series. We habitually muddle together this creative advance, which we experience and know as the perpetual transition of nature into novelty, with the single time series which we naturally employ for measurement. The various time series each measure some aspect of the creative advance, and the whole bundle of them express all the properties of this advance which are measurable. The reason why we have not previously noted this difference of time series is the very small difference of properties between any two such series. Any observable phenomena due to this cause depend on the square of the ratio of any velocity entering into the observation to the velocity of light. Now light takes about 50 minutes to get around the Earth's orbit, and the Earth takes rather more than 17,531 half-hours to do the same. Hence, all the effects due to this motion are of the order of the ratio of 1 to the square of 10,000. Accordingly, an Earth-man and a Sun-man have only neglected effects whose quantitative magnitudes all contain the factor 1 over 10 to the 8th. Evidently, such effects can only be noted by means of the most refined observations. They have been observed, however. Suppose we compare two observations on the velocity of light made with the same apparatus as we turn it through a right angle. The velocity of the Earth relative to the Sun is in one direction. The velocity of light relatively to the ether should be the same in all directions. Hence if space when we take the ether as at rest means the same thing as space when we take the Earth as at rest, we ought to find that the velocity of light relatively to the Earth varies according to the direction from which it comes. These observations on Earth constitute the basic principle of the famous experiments designed to detect the motion of the Earth through the ether. You all know that, quite unexpectedly, they gave a null result. This is completely explained by the fact that the space system and the time system which we are using are in certain minute ways different from the space and the time relatively to the Sun, or relatively to any other body with respect to which it is moving. All this discussion as to the nature of time and space has lifted above our horizon a great difficulty which affects the formulation of all the ultimate laws of physics, for example, the laws of the electromagnetic field and the law of gravitation. Let us take the law of gravitation as an example. Its formulation is as follows. Two material bodies attract each other with a force proportional to the product of their masses and inversely proportional to the square of their distances. In this statement the bodies are supposed to be small enough to be treated as material particles in relation to their distances, and we need not bother further about that minor point. The difficulty to which I want to draw your attention is this. In the formulation of the law, one definite time and one definite space are presupposed. The two masses are assumed to be in simultaneous positions. But what is simultaneous in one time system may not be simultaneous in another time system. So according to our new views, the law is in this respect not formulated so as to have any exact meaning. Furthermore, an analogous difficulty arises over the question of distance. The distance between two instantaneous positions, i.e. between two event particles, is different in different space systems. What space is to be chosen? Thus again the law lacks precise formulation, if relativity is accepted. Our problem is to seek a fresh interpretation of the law of gravity in which these difficulties are evaded. In the first place, we must avoid the abstractions of space and time in the formulation of our fundamental ideas, and must recur to the ultimate facts of nature, namely, to events. Also, in order to find the ideal simplicity of expressions of the relations between events, we restrict ourselves to event particles. Thus the life of a material particle is its adventure amid a track of event particles strung out as a continuous series or path in the four-dimensional space-time manifold. These event particles are the various situations of the material particle. We usually express this fact by adopting our natural space-time system, and by talking of the path in space of the material particle as it exists at successive instants of time. We have to ask ourselves, what are the laws of nature which lead the material particle to adopt just this path among event particles and no other? Think of the path as a whole. What characteristic has that path got which would not be shared by any other slightly varied path? We are asking for more than a law of gravity. We want laws of motion and a general idea of the way to formulate the effects of physical forces. In order to answer our question, we put the idea of the attracting masses in the background, and concentrate attention on the field of activity of the events in the neighborhood of the path. In so doing, we are acting in conformity with the whole trend of scientific thought during the last 100 years, which has more and more concentrated attention on the field of force as the immediate agent in directing motion, to the exclusion of the consideration of the immediate mutual influence between two distant bodies. We have got to find the way of expressing the field of activity of events in the neighborhood of some definite event particle E of the four-dimensional manifold. I bring in a fundamental physical idea which I call the impetus to express this physical field. The event particle E is related to any neighboring event particle P by an element of impetus. The assemblage of all the elements of impetus relating E to the assemblage of event particles in the neighborhood of E expresses the character of the field of activity in the neighborhood of E. Where I differ from Einstein is that he conceives this quantity, which I call the impetus, as merely expressing the characters of the space and time to be adopted, and thus ends by talking of the gravitational field expressing a curvature in the space-time manifold. I cannot attach any clear conception to his interpretation of space and time. My formulae differ slightly from his, though they agree in those instances where his results have been verified. I need hardly say that in this particular of the formulation of the law of gravitation, I have drawn on the general method of procedure which constitutes his great discovery. Einstein showed how to express the characters of the assemblage of elements of impetus of the field surrounding an event particle E in terms of 10 quantities, which I will call J sub 1,1, J sub 1,2 equals J sub 2,1, J sub 2,2, J sub 2,3 equals J sub 3,2, etc. It will be noted that there are 4 spatiotemporal measurements relating E to its neighbor, P, and that there are 10 pairs of such measurements if we are allowed to take any one measurement twice over to make one such pair. The 10 J's depend merely on the position of E in the four-dimensional manifold, and the element of impetus between E and P can be expressed in terms of the 10 J's and the 10 pairs of the 4 spatiotemporal measurements relating E and P. The numerical values of the J's will depend on the system of measurement adopted, but are so adjusted to each particular system that the same value is obtained for the element of impetus between E and P, whatever be the system of measurement adopted. This fact is expressed by saying that the 10 J's form a tensor. It is not going too far to say that the announcement that physicists would have in future to study the theory of tensors created a veritable panic among them when the verification of Einstein's predictions was first announced. The 10 J's at any event particle E can be expressed in terms of 2 functions, which I call the potential and the associate potential at E. The potential is practically what is meant by the ordinary gravitation potential, when we express ourselves in terms of the Euclidean space in reference to which the attracting mass is at rest. The associate potential is defined by the modification of substituting the direct distance for the inverse distance in the definition of the potential, and its calculation can easily be made to depend on that of the old-fashioned potential. Thus the calculation of the J's, the coefficients of impetus, as I will call them, does not involve anything very revolutionary in the mathematical knowledge of physicists. We now return to the path of the attracted particle. We add up all the elements of impetus in the whole path, and obtain thereby what I call the integral impetus. The characteristic of the actual path as compared with neighboring alternative paths is that in the actual paths the integral impetus would neither gain nor lose if the particle wobbled out of it into a small, extremely near alternative path. Mathematicians would express this by saying that the integral impetus is stationary for an infinitesimal displacement. In this statement of the law of motion, I have neglected the existence of other forces, but that would lead me too far afield. The electromagnetic theory has to be modified to allow for the presence of a gravitational field. Thus Einstein's investigations led to the first discovery of any relation between gravity and other physical phenomena. In the form in which I have put this modification, we deduce Einstein's fundamental principle as to the motion of light along its rays, as a first approximation, which is absolutely true for infinitely short waves. Einstein's principle, thus partially verified, stated in my language, is that a ray of light always follows a path such that the integral impetus along it is zero. This involves that every element of impetus along it is zero. In conclusion, I must apologize. In the first place, I have considerably toned down the various exciting peculiarities of the original theory, and have reduced it to a greater conformity with the older physics. I do not allow that physical phenomena are due to oddities of space. Also, I have added to the dullness of the lecture by my respect for the audience. You would have enjoyed a more popular lecture with illustrations of delightful paradoxes. But I know also that you are serious students, who are here because you really want to know how the new theories may affect your scientific researches. End of section 8.